Hi, I'm John, and I am a PhD student at the University of Colorado Boulder with the Assured, Reliable, and Interactive Autonomous Systems group. I'd like to tell you about our work towards an end-to-end framework for data-driven verification of unknown dynamical systems. Performance guarantees are important for deploying safety-critical systems. These guarantees can be generated through formal verification methods on two types of performance requirements: safety and liveness. Safety is exactly that. The system should not harm itself or its surroundings. Also, the system has to do something eventually. This is liveness. Traditional methods for verifying against formal specifications rely on having high fidelity system models to perform model checking techniques. However, the verification results are only applicable to the considered model. If we have a system with an unknown component, such as a black box autopilot or a simplified model, then verification results do not hold for the underlying system. We want a way to connect this model to the underlying system to extend the result. Data-driven methods are gaining traction in overcoming these challenges. Take, for example, this autonomous underwater vehicle in a 2D space. While we do not have a full dynamics model, we can collect measurements to regress a model and bound the regression error. In this example, we are interested in finding initial states and resulting trajectories that satisfy and violate the property "do not enter A until B is entered." Our proposed framework can generate guarantees using a set of noisy state action measurement data from a system. To account for the modeling uncertainty, we generate probabilistic guarantees with respect to these system properties. By taking this uncertainty into account, the verification results on the regression model are valid for the underlying system. The framework consists of three primary components: a Gaussian process regression model of the dynamics, an interval Markov decision process abstraction, and a solver for the IMDP. We get tight probabilistic error bounds from GPU regression using RKHS-based analysis, and use these errors to define the transition bounds of the IMDP. The best and worst case system behavior depends only on the one-step transition probabilities that are computed by modeling it as a two-player game. In this game, one player chooses actions and the other chooses a feasible transition probability distribution. The verification result generally consists of three sets: a set that is guaranteed to satisfy the property, a set that is guaranteed to violate the property, and a set where no guarantees can be made due to high uncertainty. We can generate results for linear, nonlinear, and multimodal switched systems. This framework is our first attempt to connect machine learning regression to the verification of dynamical systems in safety-critical scenarios. We have a lot of exciting ideas for next steps, including online verification, controller synthesis for learned systems, and exploring other regression methods. Thank you for listening.